Hello students, welcome to our channel Math with GG. In today's lecture, we are going to learn type 2 of curve tracing, that is curve tracing of parametric curve. If you have not watched our previous two parts of curve tracing, we recommend go to the videos and watch this. The links of the videos are given in the description. If you have not subscribed our channel, please subscribe our channel Math with GG. Let's start with the today's topic, curve tracing of parametric curves. For curve tracing of parametric curves, there are 5 rules. Rule number 1 is limitation of the curve. We will try to find if there is any limitation to the curve for both the axes x as well as y. If the limitation is there, we will apply that limitation. The second is symmetry. We'll check the curve is symmetric about x-axis or y-axis or both coordinate axis, or there is some another possibility about some line or opposite quadrants. We will check in rule number 2. Third point, origin, whether the curve passes through origin or not. Rule 4, special points. We will check the derivatives of points where the derivative is 0 or infinity. This will give you the special points. And the last, rule number 5, table. This value gives us how to draw the region and where to draw the region. So, these are the 5 rules for parametric curves. Let's start with the example of curve tracing of type 2 curves, that is parametric curve. Example 1, trace the curve x raised to 2 by 3 plus y raised to 2 by 3 equal to a raised to 2 by 3. Now if you observe, though the curve is in xy, but the powers of x and y are rational numbers, hence we cannot trace the curve using Cartesian type. So we have to convert this curve into parametric curve by substituting both the values of xy in new variable t or in parameter t. So if you observe, the term is like x raised to 2 by 3 plus y raised to 2 by 3 equal to a raised to 2 by 3. We have one identity, sin square theta plus cos square theta equal to 1. So if we use the term for substitution, x is equal to a cos cube theta and y is equal to a sin cube theta. Now, if we replace this value in the given equation, the equation becomes a raised to 2 by 3 cos cube raised to 2 by 3. So this 3 get cancelled. So we get a raised to 2 by 3 cos square theta plus a raised to 2 by 3 sin square theta. If we take a raised to 2 by 3 common, hence we get cos square theta plus sin square theta, that is 1, that is the right hand side. So with the help of this substitution, both x and y are replaced in terms of theta, that hence theta is our parameter, hence this curve is converted into parametric curve. Now let's start with the first rule, limitation of the curve. Now if we observe, x and y are in terms of trigonometric function sin theta and cos theta, and we know that the range of sin theta and cos theta is -1 to 1. That is, the least value of sin theta and cos theta is -1 and the greatest value of sin theta and cos theta is +1. So if we apply both these cases, we get the limitation for the curve. So if we take the least value of cos theta, that is -1, so -1 whole cube will be -1. Hence the least value of x will be -a, as well as the least value of sin theta is -1. Hence the least value of y is -a. Similarly, if we take the greatest values of sin theta and cos theta, that is 1, the cube will give you again 1. Hence the least and greatest value of x and y is a. Therefore, as least and greatest values of sin theta and cos theta are -1 and 1 respectively. Therefore, least and greatest values of x and y are -a and a. So this gives us the limitation to both the axes, both the coordinates of x and y. That means x will lies between -a to a, y also lies between -a to a. So we get a square with the help of this limitation. So whatever the curve we get, it will be lying in that square. So this is our rule number 1, symmetry. Now, rule 2, symmetry. For symmetry, in parametric curve, we have to check whether the function is even or odd. To check x and y even or odd, we will replace theta by minus theta in both the terms. So, for x, if we replace theta by minus theta, we know that cos of minus theta is cos theta. Therefore, cos cube of theta will be same. So x is not changing. That is, x is even. And for y, if we replace theta by minus theta, we get sine of minus theta is minus sine theta. Hence, y will be minus times a sine cube theta. So y changes by sine. Therefore, y is odd. So x is even, y is odd. So if we get such case, x is even function, y is odd function, then the curve is symmetric about x-axis. So rule 2, symmetry, replace theta by minus theta. Therefore, x is equal to a cos of minus theta whole cube. We know that cos of minus theta is cos theta whole cube. So we get a cos cube theta, and which is equal to x. That is, the sign of x doesn't change. Therefore, x is even function. Similarly, for y, if we replace, so y is equal to a into sine of minus theta whole cube. Sine of minus theta is minus sine theta. So minus sine theta whole cube, that is equal to minus a sine cube theta. So y changes by sign, therefore y is an odd function. Y is an odd function. Therefore, x is even function, y is odd function. Therefore, curve is symmetric about x-axis. Now we have to check whether the curve is symmetric about y-axis also. Now, as the curve is symmetric about x-axis, we have to check also whether the curve is symmetric about y-axis. What we will do, we'll replace theta by pi minus theta. So, if we replace theta by pi minus theta, we get x is equal to a cos of pi minus theta whole cube. Since cos of pi minus theta is minus cos theta, so this is minus cos theta whole cube, that is minus a cos cube theta, and for y, a into sine pi minus theta whole cube. Sine pi minus theta is sine theta, so we get a sine theta whole cube, that is equal to a sine cube theta. Now, if you observe, x changes by sign and y remains unchanged. If by replacing theta by pi minus theta, we get x changes by sign only and y remains unchanged, curve is symmetric about y-axis. Therefore, curve is symmetric about y-axis also. So, in this rule, we have studied the symmetry about the curve. Now, let's study the rule number 3. Now rule number 3 is origin. We have to check whether curve passes through origin. If for some value of theta both x and y equal to 0, then curve will pass through origin. But if you observe, the function x and y contains cos theta and sin theta, and we know that sin theta and cos theta are not 0 for same value of theta. Therefore, for any value of theta, both x and y are not 0 simultaneously. Therefore, curve do not passes through origin. So as we don't get any value of theta for which both x and y are 0 simultaneously, hence the curve do not pass through origin. Now, in rule number 5, we are going to learn how the curve will intersect x-axis or y-axis, or what are the other points where curve cuts the coordinate axis. Now, let's study rule number 4. Rule 4 is special points. To check whether the curve are having special points, we'll first find out the derivative of the curve with respect to x, that is dy by dx. As x and y are parametric, so first we'll find out dx by d theta and dy by d theta. So differentiating x with respect to theta, we get a derivative of cos cube theta is 3 cos square theta into derivative of cos theta, that is minus sin theta. Simplifying, we get minus 3a sin theta cos square theta. Similarly, if we differentiate y with respect to theta, we get dy by d theta equal to a 3 sin square theta into derivative of sin theta cos theta. So 3a sin square theta cos theta. Therefore, dy by dx equal to dy by d theta upon dx by d theta. So, if we substitute these values, we get 3a sin square theta cos theta upon minus 3a sin theta cos square theta. So, this 3a get cancelled, sin theta get cancelled, 1 cos get cancelled, so we get sin theta upon cos theta. Now, let's check the values of theta for which dy by dx is 0 or infinity. So, if we take dy by dx equal to 0, therefore, we get sin theta equal to 0. As dy by dx is in the ratio sin theta upon cos theta, so dy by dx is 0. It is happening if and only if the numerator is 0. So, sin theta equal to 0. So, we know that for if sin theta equal to 0, then for any value of n pi, where n is a integer, we get sin theta equal to 0. So sin theta equal to 0 implies theta equal to n pi, where n is integer. Similarly, if we take dy by dx equal to infinity. Now, the ratio is infinity. That means sin theta minus sin theta upon cos theta equal to infinity. This will happen if and only if denominator is 0. Therefore, this will imply cos theta equal to 0. And we know that odd multiples of pi by 2 will give us cos theta equal to 0. So, theta is equal to 2n plus 1 into pi by 2, where n is integer. So, these are your special points of the curve. Now, last rule, rule number 5, table of theta. In rule number 5, we will study for different values of theta, what are the values of x and y. This will give us the nature of the curve as well as the curve where it cuts coordinate axis. So, we will take the values of theta between 0 to 2 pi with a difference of 90 degree or pi by 2. So, let's start. So, theta 0, pi by 2, pi, 3 pi by 2 and 2 pi. Now x and y. So if we substitute the value of theta in x, so cos 0 is 1, hence x is equal to a. For pi by 2, cos pi by 2 is 0, x is 0. For pi, cos pi is minus 1 whole cube will be minus 1, so x is minus a. For 3 pi by 2, again cos is 0, therefore x is 0. For 2 pi, cos 2 pi is 1, hence x is a. Similarly, for sin 0 is 0, therefore y is 0. Sin pi by 2 is 1, therefore y is a. Sin pi is 0, therefore y is 0. Sin 3 pi by 2 is minus 1 cube, again minus, so minus a, and sin 2 pi is 0. So this is the rule number 5, table of theta. Now let's summarize all the rules and we'll draw a rough sketch of this curve. Let's summarize all the rules and then draw a rough sketch. In rule number 1, for limitation we have studied the curve is having limitation for both x and y, that is least value as minus a, greatest value as a for both x and y. Rule 2, symmetry, curve is symmetric about both xy axis. Rule 3, curve do not pass trace through origin. Rule 4, theta equal to n pi and theta equal to 2n plus 1 pi by 2 are the special points. And from the table, the curve passes through a comma 0, 0 comma a, minus a comma 0 and 0 minus a. Let's draw a rough sketch. Now, as the curve is having limitation a and minus a to both axes, let's limit our region to these 4 points. Now, in rule number 4, theta equal to n pi and theta equal to 2n plus 1 pi by 2 are both special points. So, if you observe, all these points are special points and the nature of the tangent at these points is unique. Hence, all the 4 points are cusp. So, if we draw the sketch, so the rough sketch of this graph as it is symmetric about both axes. So this is the rough sketch of the example number 1, x raised to 2 by 3 plus y raised to 2 by 3 equal to a raised to 2 by 3. This curve is called as asteroid. If you look at the shape, because of this shape, the curve is known as asteroid. In next video, we will learn the second example of the type 2 curve, that is parametric curve. If you have not subscribed our channel, please subscribe. If you like the video, please share with your friends and subscribe our channel Math with JG. Thank you.